All right, back again. Chemistry 3202, Course Overview Review, Unit 2, Section 2, Lesson 3 this time. We're going to talk about acid-base strength and how it relates to an equilibrium expression Ka for acids and the equilibrium expression Kb for bases. This is Chapter 15 of your textbook, page 582, and the associated pages. 582, 585, and of course talking about the Ka, 587, and 592 for Kb. A few related homework questions you can give a try here and see if you can pick some sense out of them. There we go. Don't forget now, take advantage of our online tutor and the online resources, and if you have any questions on this stuff, don't forget to drop me a line through the discussions, and I'll try to address it at the beginning of the next lesson. Here are the outcomes for this lesson. We want to talk about the strength of an acid versus the concentration of an acid. Both of these terms sometimes are used interchangeably, and that's not correct. All right, they have two different meanings, so let's look at the meaning of strength versus concentration. Now, the strength of an acid depends on the amount of hydronium that it's going to produce, or if it's a base, the amount of hydroxide that it's going to produce. And we looked at that before with our acid-base table, and we looked at the percent reaction or the percent ionization for the strength of the acid or base. In the case of the base, it would be the percent dissociation. So a strong acid would be a species that produces stoichiometric equivalent amount. So that would be a 1-to-1 ratio. And we said strong acids, because they are 100% ionized, then the concentration of the H3O plus is going to be equal to the concentration of the acid, because every last one of the acids are broken down. Same thing, I guess, is true for bases like sodium hydroxide. These guys would produce 1-to-1 stoichiometric equivalents of hydroxide ions because they're 100% dissociated. So in this sense, then, we say that the products are favored if we look at the acid ionization constant, an equilibrium perspective. Now, Ka is just a specialized equilibrium expression when it relates to an acid. So in this case, if we have 100% ionization, that means the acid is driving forward 100% of the time, which means, of course, any equilibrium expression that we would write here would have a very large K value, which would be pointing towards the products. So every one of these acids that are strong are going to have Ka values greater than 1. Let's look at our acid-base table just to show you. In our acid-base table, I'll just enlarge this a little bit. Okay, in our acid-base table, the 6 strong acids are these guys on top here. Okay, there's your 6 strong acids. They're 100% ionized. And you look at the values of their Kas. And each of these is a positive exponent, 10 to the 9, 10 to the 9, 10 to the 5, 10 to the plus 3, 10 to the plus 1. So every one of these guys, because it's a strong acid, Ka is very much greater than 1. So these guys all push forward to a great extent. Okay. Now if we look at the weak acids, we're saying, all right, weak acids were the ones that were classified as species that have a less than 100% ionization. So we see that they're less than 100%, which would mean that these guys really don't want to break down. And if we look at it from an equilibrium perspective, if they don't want to break down, that means they don't want to go forward. They tend not to ionize. So the K is going to be less than 1, so we're going to be falling back and favoring the reactants. If we go back and look at our acid-base table here for the weak acids, what we notice is that these guys down here are the weak acids, because their ionizations are much less than 100%. So all of these acids, now again, this is Ka, every single one of these Ka values, look at the exponent, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. So every single one of these weak acids below this line, K is going to be less than 1, which means every single one of these guys favor not ionizing. All right, they prefer not to ionize, and that's why they're weak acids. So in terms of their strength is based upon their ability to ionize. If they're strong, then they're 100% ionized. K is very large. If they're weak, then they're less than 100%. K is very small. Okay. Now we want to be able to compare this with concentration. Now concentration has a different meaning. Concentration refers to the number of moles dissolved per liter of solvent. So in this sense, you can have, the higher the number of moles, then the more concentrated it's going to be. The fewer the number of moles, the more dilute it's going to be. Now, lots of times we refer to something as being very strong. Like if you had frozen orange juice and you take a sample of it right out of the frozen can before you add any water to it, you'll say, oh my God, that's awful strong. But no, what you have to be saying is it's not strong. It's very sweet and very sour. It's very concentrated. That's what's causing it to have those properties. It's very concentrated. When you add water to it, you would say, well, it's pretty weak now because it's not as sweet as it used to be. But that's not the correct use of the term. What you should be saying is when you add water to it, now you've made it more dilute. All right. So dilute versus concentrated is reserved to express the number of moles per liter. Strong versus weak refer to an acid's ability to ionize. Okay, so big difference, and has a big difference. Are these two terms interchangeable? And from what we've just said, the answer should be no, they are not interchangeable. We cannot use strong and weak in the same context. Concentrated or dilute and strong and weak in the same context. They mean two different things. So we can have an acid or a base that's strong but yet dilute. So for instance, I could give you hydrochloric acid, and its mere identity, the fact that it's hydrochloric acid, makes it a strong acid. It's going to be 100% ionized. Now I can take a little tiny bit of that hydrochloric acid and put it in a lot of water, in which case I've just made a dilute solution. There's very few moles per liter. So therefore we have a strong acid that's been diluted by a lot of water. So here's an example then. We would say that if the concentration of hydrochloric acid was 1 times 10 to the minus 4, that's not very much. That's 0.0001 moles per liter. Then it's a strong acid because it's hydrochloric. It's 100% ionized. But because the concentration is so small, we would refer to it as dilute. All right, and it's also possible to go the other way. We could have a very weak acid that's very concentrated, and an example of that would be, say, vinegar, ethanoic acid. Its position on the acid-base table tells us that it's a weak acid. It's only like 1% ionized. But yet look at the concentration. This is very concentrated compared to this guy up here, 17 moles per liter. This stuff is very, very thick. It's just like syrup when you pour it out, very heavy. All right, so it's a very concentrated, weak acid. There we go. So that's the differences in the terms. All right, so no, you cannot use them interchangeably. And I should put that there. No, they are not. Okay, we want to be able to identify strong and weak acids, and we want to be able to do some tests and say, okay, I've got an unknown acid on the table. We know that when we test it, acids turn blue litmus red. So we've done our litmus test and we say, yeah, okay, this is turning blue litmus red, so it's an acid. But how do we know if it's acetic acid, which is a weak acid, or if it's hydrochloric acid, that's a strong acid? How do we know which is which? Well, we could do a number of tests here, and the tests we've got here, okay, we say we know acids react with metals. And we can say that the stronger the acid, the more the reaction is going to be. And this should make sense because hydrochloric acid has a very, very strong desire to want to ionize. So as soon as that comes in contact with the metal, it's going to react much more quickly than, say, the vinegar, which is a weak acid, which really doesn't want to ionize. So when it comes in contact with the metal, it says, yeah, right, maybe. Right? It really doesn't want to react that fast. It will, but it's going to be very slow because it's weak. All right? So we're looking at this and we're saying if we have the same amount of concentration here, 1 mole per liter hydrochloric versus 1 mole per liter acetic, the hydrochloric acid is going to react faster because it's going to want to ionize more. And of course we have to use the same concentrations because we want to have some kind of control in our observations. We need to say, well, the concentrations are the same, so that's not the factor. The only factor that's different is the strength of the two acids. Okay, and here's an example, of course, where we react magnesium with hydrochloric acid. All right, producing hydrogen gas. This is going to be very fast in comparison, and this is the exact same reaction using magnesium and 1 mole per liter vinegar, acetic acid. And very similar reaction, we're going to produce hydrogen gas, but this is going to be a very, very slow reaction because this is a weak acid. So that's one way we could test the substances. Now we have to do a comparison. If we just have one acid, it's going to be very difficult to say if it's fast or slow. We always have to be able to compare it to some other. So we like to compare 2 types of acids here. All right. We could use universal pH paper. So if you have a goldfish tank or something like that and you really want to know what the pH is, we can get a range of pHs using universal pH paper, which uses indicators, and we'll talk about that in another lesson. But the indicators would change color at varying pHs. So we're looking at a situation where we have, again, 2.1 mole per liter solutions. One solution is found to have a pH of 1.5. The other has a pH of 3. Now, because we have the exact same concentration, again, we want control, we're saying that when we take the pH of something, it's the log of the hydronium, log of H3O+. So the more H3O+ we have, the lower the pH is going to be. The closer to 0 we're going to be for our pH. pH 1 is much more H3O+ than, say, pH 2. So the idea being here is that because we have the same concentration, this acid here, A, has a much lower pH, so therefore it's producing more H3O+. So it's ionizing to a larger degree. This guy right here, B, has a pH of 3, which means there's less H3O+, which means it's ionized less than acid A. So acid A would be the stronger of the 2. Okay? So we're comparing the same concentration. There we go. So the one that produces more hydronium is the one that's ionizing more, and therefore it's going to have a lower pH. Now, we can't say if it's a strong acid or a weak acid, can we? All we can say is that one is stronger than the other. No, it's going to be very difficult to say if it's a strong acid or a weak acid because that's going to also depend on the concentration, the moles per liter. So something else comes in play. But when we compare 2 acids, A and B, we can figure out which one is the stronger of the 2. And the other one here is based on the same sort of principle. This time we're going to use a pH meter, which is going to measure the H3O+ concentration. And when we do this, of course, it's for the same reasons in number 2. The stronger acid is the one that's going to ionize more, and therefore that's the one that's going to be the stronger because it's making more H3O+. And again, we cannot really identify if it's a stronger or weak acid. What we're doing is simply figuring out which one is the stronger of the 2. All right, there we go. Okay, ionization constants. Now this is just another special case of equilibrium, and we've done this before, and we're looking at this and we're saying, all right, let's write an equilibrium expression for this particular reaction. And we're saying, all right, well, the very first thing we got to do is cross out the water, because the water is a liquid, and we don't use liquids or pure solids in equilibrium. They don't change their concentration, so therefore they're going to be a non-factor. So we can cross that out, and we can say, all right, we can do this. The equilibrium expression here is going to be products over reactants, sorry. All right, so products over reactants. These guys are all power 1s, and that's the beauty part of Kas and Kbs is that we always generally have a single proton transfer. Therefore, everything is always going to be a 1-to-1 ratio. So in this case, our equilibrium expression is going to be products over reactants, and in this case, the Ka for the acid is always going to involve H3O+ as a product. That's what makes it an acid, isn't it? According to Bronsted-Lowry, we're going to get this H3O+ here. And that's what makes it the acid, of course. And because it's a specialized equilibrium, we just denote it with a subscript A, referring to the fact that it's equilibrium for an acid reaction. There we go. Okay, so that's easy enough. Okay, we can also look at a reaction for a base. In this case, we're going to take ammonia and we're going to react it with water, and we produce NH4+ and OH-. So now we've got a base being produced here, and again, we just take out the water because that's a liquid. We don't include it. So in this case, again, it's going to be products over reactants, and we denote this with a B because we're referring to a special equilibrium for the base. And you notice here that the hydroxide is always going to be on the top, and that's going to express a base. Up here we had the hydronium on top, which made it an acid. This guy has the hydroxide on top, which makes it a base. Okay, there we go. Okay, so we want to write the expression for, say, sodium cyanide. So let's say they give us sodium cyanide. We want to write some kind of equilibrium expression for this, and we really don't know what it is at this stage. So we're looking at sodium cyanide and saying, hey, well, this is sodium cyanide. There's no hydrogen or nothing there, so chances are it's probably not going to be a base. We do know that it's an ionic compound, so this should start looking again like writing a Bronsted-Lowry equation. Remember that from a couple of lessons back, how to write a net ionic equation for an acid-base reaction. So we're looking at this and we're saying, hey, that's an ionic compound. That's going to be 100% dissociated, so I'm going to get some sodium ions and some cyanide ions. And what I'm looking at here now is the fact that I'm mixing that with water. And in the case that we have water present here, because it's an aqueous solution, the water is the only thing in this container that can act as an acid. So that's going to be my acid in this reaction. And if we look at cyanide and water here, cyanide is the one that's going to be the base, even though water can be a base. The cyanide ion is much stronger. Check your acid-base tables. So we've got our acid and our base selected. So what we're going to do here now is write the equation showing cyanide acting as a base. It's subtracting the hydrogen from the water, and we're going to get HCN and OH minus. So now we can write the equilibrium expression. And right off the bat now you should be saying, okay, there's OH produced there, so this is going to be a KB. This is a basic equation, and it's going to be HCN, products over reactants. There we go. Omit water because it's a liquid, and that's our KB expression. So that's a neat little question for a public exam, just to see if you can write the Bronsted-Lowry equation and then be able to write the KB. All right, a few notes here on Ka and Kb. Ka and Kb are just special forms of the equilibrium constant, just like Kw, that was the expression for water. Ka now is an expression for an acid. Kb is the expression for the base. The Ka values for common acids are provided on the acid-base table, so let's just go back here. And you notice here from our acid-base table that these guys on this side are the acids. These guys here are the conjugate bases of these acids. So this is when, say, HClO4 gives up its hydrogen and it produces this as a conjugate base. The values listed on the table, even though they're on the base side of the table, these are all Kas. So these are the expressions, the values for the acids. So these numbers should probably be over here somewhere. They should have probably put them next to the percent ionization. But these values are all for Ka. There are no Kb values given on the table, and I'll show you how you can get the Kb's now in a second. Okay, and number 3 here, Kb values for conjugate bases can be derived from this expression here. They just did a little bit of mathematics, and they're saying Kw, we know what that is, that's 1 times 10 to the minus 14, is equal to the Ka times the Kb. So this is a constant. Kas can be arrived at you can get these from the acid-base table, and therefore we can calculate Kb. So let's have a look at one. Okay. Before we do that, we've got a few acids listed here. We're noticing we have nitric acid, hydrofluoric acid, hydrosulfuric acid, and boric acid. And we simply went to the table and listed their formulas, and we then listed the Ka values of each acid as we went down the table. And you notice that we're going from a +1 to a -4 to a -7 to a -10. So as we go down the table, we're noticing that these guys up here are stronger acids, and as we start going down the table, they get weaker and weaker and weaker because the percent reaction is getting smaller and smaller and smaller. But we can see this and we can say that, well, not only is the percent reaction getting smaller and smaller and smaller, so is the value of K. And again, we're looking at the exponent here. K is greater than 1 here, which makes it a strong acid. Each of these guys, K is less than 1, K is much less than 1, K is much, much, much less than 1. So as we go down the table, we're getting weaker and weaker and weaker. So the smaller the Ka, the weaker the acid. Okay, smaller the Ka, the weaker the acid. And here's an example. We're taking this, we're saying, okay, let's look at hydrofluoric acid. We write the equilibrium expression here, reacts with water to produce fluoride ion and H3O+. The Ka value of this can be arrived at from the table, 6.4 times 10 to the minus 4. I want to be able to find the Kb for fluoride, because if I look at my table right here, here's hydrofluoric acid. This is the value for Ka. This is for hydrogen fluoride. I want to figure out what the Kb value is for fluoride. So I simply do my little bit of mathematics here, and I say, all right, well, Kw is equal to Ka times Kb, so let's rearrange it. Kb is Kw over Ka. So I put my values in, and I calculate it. Now don't forget, when you're using your calculator, make sure you put your brackets around here, and don't forget to hit the exponent button, 10 exponent minus 14, and see if you can get that answer, 1.56 times 10 to the minus 11, and double check that, right? You don't want to lose marks because you don't know how to use your calculator. Okay, comparisons of Kas and Kbs. Now, what they're going to do here is play around with some numbers for you guys on the exam and whatnot. So what we're saying is, the larger the Ka value, the stronger the acid. And that should make sense because the larger the Ka, the closer we are to the top. Right? The larger the Ka, the closer we are on the top on that table. So therefore, if we have a great big Ka, if we do the calculation, remember if we do Kw equals Ka times Kb, and if we want to solve for Kb, it's going to be Kw over Ka. If Ka is large, that means Kb is going to be very tiny. So it's an inverse relationship for the most part. So the stronger the acid, the weaker the base. Let's go and look at our table. I'm looking at this over here and I'm saying, well, these guys are all the strong acids right here. Look at the size of Ka. These are very, very, very strong acids. But if you look at the position of these guys, these are the weakest bases, because remember now, as we go down on the acid side, we get weaker. And these guys are stronger on this side. I should have went the other way. So as we go up, we're getting stronger. On the base side, as we go down, we're getting stronger. As we start moving down these bases, we get stronger bases. And these guys up here would be the weakest of all. All right, the weakest bases. So what we're seeing then is that if the Ka is very big, because they're the strongest acids, these guys are the weakest bases, so they must have the smallest Kbs. All right, so a big Kb would be a strong base. These guys down here would have bigger Kbs because they're stronger. These guys up here have smaller Kbs because they're weaker bases. And let me just clean this up a little bit. And we'll be back in a sec. There we go. Okay, so going back to what we were saying then, if we want to be able to compare these guys, the larger the Ka, the stronger the acid, and then conversely, the conjugate base is considered to be very, very weak, and therefore it's going to be very small. All right. If the Ka is larger than the Kb, so if, in other words, if the acid is stronger than the base, if the acid is stronger than the base, then the reaction is going to move forward. Okay. So let me just get rid of this here now. And what we're saying then is that if K, oh my Lord, look the size of that pencil. Let's fix this up again. If Ka is bigger than Kb, look at the way the arrow is pointing in that direction. It's going to move forward. The acid is going to want to ionize. So Ka is greater than Kb. All right, so let's have a look at some examples here. The nitrous acid and the nitrite ion. So here we go. In this particular reaction, we got nitrous acid, HNO2. It's a weak acid, HNO2. Don't confuse it with nitric acid, which is HNO3. This acid is probably going to donate its hydrogen to water, and we're saying that we're going to produce nitrite and H3O+ here. And we know what the Ka of this one is. The Ka is 7.2 times 10 to the minus 4. You get that from the table. What we want to do is look at this reaction and say, is this going to push forward? Is nitrous acid a strong enough acid to make this push forward? And what we can do here is calculate Kb. Kb is Kw over Ka. And lo and behold, we get 1.3 times 10 to the minus 11. This is the Ka, this is minus 4. This is the Kb, it's minus 11. So this Ka value is much larger than Kb, and therefore the reaction pushes forward. Now we would have done this, okay, any questions with that? Obviously not, because you can't answer questions. Here we go. All right, we're looking at this particular reaction here, and we're saying, okay, hydrogen cyanide and the cyanide ion. So there we go. Hydrogen cyanide, again, it's a weak acid. We know the Ka value is 6.2 times 10 to the minus 10. And in this case, we're saying, okay, Kb is Kw over Ka, and we can calculate Kb, and look at that. Now it's 10 to the minus 5. 10 to the minus 10 for the acid, 10 to the minus 5 for the base. The base is much stronger. So what we're saying then is that as HCN as an acid, the cyanide has a much more desire to want to react with H3O plus here and move backwards. So this reaction is going to go in the reverse direction here. Okay? So that's what we're looking at. We're comparing Kas and Kbs. All right, we want to be able to write some expressions here. So this is generally a review of what we've just done here. So H2SO3, we're looking at this guy and saying, okay, we want to write a Ka or Kb. So we look at this and we say, all right, H2SO3, if it donates a single proton, a single hydrogen, because that's what Bronsted-Lowry says, one hydrogen at a time. So even though it has two here, we're only going to donate one of these. And when we donate one of these hydrogens, that hydrogen gets donated over there, and therefore we're producing H3O plus. So what we're going to get then is a Ka. So in this case, we're saying Ka is going to be HSO3 times H3O plus, there it is on top, divided by H2SO3. And again, one hydrogen is all that gets transferred. Okay, here's another example then. This is sodium borate. Now we know that sodium borate is an ionic compound, so it's going to be 100% ionized. It's going to produce sodium ions and borate ions. The sodium ions don't do anything. And again, it's going to be a single hydrogen transfer this way, which makes the borate a base. So the Kb this time is going to be HbO3 2 minus times OH minus divided by BO3. And each time we're ignoring the water because it's a liquid. Another example, here's another one, hypochlorous acid, HClO2. We simply look at this guy and we say, okay, that's an acid. It's going to donate a single hydrogen, so this is going to be a Ka value. So that gets transferred over there. So this is a Ka, and in this case it's going to be ClO2 minus times H3O plus. There's H3O plus on top again because it's a product, and then HClO2. Okay, Kbs have OH minus on top, Kas have H3O plus. And here finally is the last one. This is potassium thiocyanate. And again, it's an ionic compound, and you may want to just check the acid-base table to see where this SCN ion fits in. Or if you can't find it there, then you can probably find it on your table of complex ions. And we're saying that this guy is going to be 100% dissociated because it's ionic. And we're going to produce some thiocyanate ion here, SCN minus, in which case this guy acts as a base because it's going to attract that hydrogen. So what we're going to see then is a Kb here, which is going to be HSCN and SCN minus, products over reactants. There we go. And everything is to the power 1 here, again, because Bronsted-Lowry says everything is a single hydrogen transfer, so everything is a 1-to-1 ratio. So when you write Kas and Kbs, they should always end up being, everything should be to the power 1. Here we go. Okay, here's a couple public exam questions I couldn't refuse to put here. They like to play around with this concept of strength and positioning on the table and things like that. And they like to play around with twisting it around and writing it in terms of acids or writing it in terms of the base. So in this particular reaction or question is saying, which Ka value represents a solution with the lowest pOH? Okay. Well, what we got to watch out for here is we're saying which one is going to be, which acid is going to have the lowest pOH. Well, if we're just giving you a pOH, then what we have to do is subtract 14 to get pH. So now we're saying, okay, we want an acid with a pH of 12. Well, that's a really weak acid. If I wanted a strong acid, I would have a very low Ka. So I'm looking for the smallest Ka. That would give me the weakest acid, which is going to give me an acid, a pH up around 12, not very acidic at all. So what we're looking at is the idea here that the higher the Ka, the bigger the Ka, this is going to be a strong acid, stronger acid. So it's going to have the lowest pH. And if we look at this guy up here with 10 to the minus 9, this is the weakest acid, in which case it's not an acid at all, it's going to be a base, and this is going to have the highest pH. And that's my answer here, A. Now another way we could have done this is we could have looked at this and we could have calculated each of these and turned them into KBs. So we could have said KB is KW over Ka, and then we could have done a comparison of KB. So that's another way we could have done this problem. So calculate each of the KBs, and then you would have looked for the strongest KB, or the strongest base, right? So that's another way you could have done that. Here's another problem. It says here's a table, and I've got my choices A, B, C, D, E, and they gave us the table. And they're saying, okay, which 4 unknown acids, the pH of a 0.1 mole per liter solution of acid is given, which conjugate base would have the lowest Kb? Okay, now remember we talked about this idea that the stronger the acid, the weaker the base, right? If the acid is high on the table, that means its conjugate base is high on the table as well, which makes it a weak base. Let's go look at our table again. So we said, if we're high on the table as an acid, that makes us strong as an acid, but this means we're the weakest base. So the larger the Ka, the smaller the Kb, and that's what we're looking for in this question. We're saying which acid is going to have the largest Ka, and we're saying, well, that's going to be the strongest acid. So the strongest acid represents the weakest base. Okay, so what we're saying then is whichever one has the lowest pH, that's the one that's making most H3O+, and that's the one that's the strongest acid, so therefore that's going to be the weakest base, and the strongest acid is going to be HY right here because it has the lowest pH. So therefore the weakest, that's what they're asking for, which would have the lowest Kb, that would be the weakest base, and that's going to be Y minus, because it's the conjugate base, right? If HY reacts with water, it's going to produce H3O+ and Y minus. So if this is the acid, that's the base. This would be the conjugate acid. This would be the conjugate base. So the weakest conjugate base is the one that's linked to the strongest acid. There we go. So tough questions, tough questions. Here's another one. This one's a difficult one as well, and saying, okay, similar to what we just did up above, it says which is the strongest acid and the strongest base in the equilibrium below. So remember now, if we're looking at this particular reaction saying we want the strongest acid and the strongest base, okay, that's a weird way of looking at it. Up above in number 17 above, they wanted the strongest acid and the weakest base. So we're looking at this and we're saying, hey, the K is much greater than 1. So this Ka is representing a very strong acid. So right off the bat, we know which one is the strongest acid. It's going to have to be Hy, because this reaction pushes forward to a great extent. So Hy is going to be the strongest acid. So one of these guys is my answer. Hz would be the weakest acid. And we said the stronger the acid, the weaker the conjugate base. So if Hy, as we did up above here, same sort of setup, if Hy is the stronger acid, then that must be the weakest base. Which means if this guy's acting as a base, it must be stronger than that guy, because that's going to be the weakest base of all, because this is the strongest acid. So therefore, the strongest base is going to be Z minus. So the answer is B. Okay, so stronger the acid, the weaker the conjugate base. All right, and that's that. Okay, don't forget to take advantage of our online tutors. Don't forget to take advantage of all the online content and materials we have there, especially the public exam review questions. Lots of good stuff there. All right, see you later. Bye-bye.